Welcome everybody to this webinar about understanding pulsations and vibrations due to reciprocating pumps. First, I'm an engineer. My name is Christian Wijns-Goemakkers and I'm an engineer at Dynaflow Research Group currently. And I'm going to talk about the pressure pulsations. So first of all, pulsations are the pressure fluctuations caused by the pump which travel through the piping system. That's a very basic definition, and that's what we will talk about for the majority of this webinar. So first of all, why is this interesting? The main problems due to excessive pressure pulsations are the shaking forces causing vibrations and fatigue failure. This is really the main issue. And other issues are reduced service life of pump valves and noise. And at the end of this webinar, you'll see that you should definitely pay sufficient attention in the design of managing pressure pulsations to prevent failures. Then a little bit about the company I work for, DRG. We're a leading engineering consulting firm and we have three main activities. The first one is engineering. The second one is software, so we have several packages involving the transient fluid calculations and piping. This also includes the pulsation analysis software we develop. And then we also have several mechanical packages. Then our last activity is training. We organize training events and then we also organize conferences, and this webinar is also part of this training activity. So a little bit more about the services in engineering consulting. We do calculations for pressure and thermal equipment and piping, fiberglass piping, and then we also do calculations for gas, compressors and pumps. And this is also where the pulsation and vibration analysis comes into play, and this is where we get our main expertise on this area from, which we will show in this webinar. We also do flow analysis and we end up with software consulting. I won't go into that much more detail about what we do, and we'll go straight into the roadmap for pulsation and vibration analysis. We'll come back to this roadmap every so now and then during the webinar, and we'll treat each aspect at its own pace. So you can see all the aspects are in there: the pump, the dampeners, the piping geometry. You can see in the middle the pulsations, and then we end up with the vibrations, which are the final result of the whole analysis. But first, let's talk a little bit about resonance. Resonance is a critical aspect when you're doing pulsation and vibration analysis. You should really have a clear understanding of what resonance is. And basically the definition is when the excitation frequency is equal to the natural frequency of the system, resonance occurs. And I've a little YouTube video here which might explain this concept a little bit better. So this is an experiment done by the University of Missouri, and it's an experiment showing resonance. So initially they have three systems going from left to right. This is a system, a center system and a right system, and each system has a different natural frequency. And the initial excitation source comes from the shaking table, and they slowly increase the frequency of the excitation until it matches one of the natural frequencies of each of these systems above. So they slowly increase it, and you can see the most right system has the lowest natural frequency, and it starts to show signs of resonance. And if they increase the frequency even more, larger resonance will occur. And you should definitely notice that even though the initial excitation displacement is relatively small, when resonance occurs, this displacement can be amplified significantly to many times larger than the initial displacement. So here you can see resonance occurs at 4 Hz, and the displacement is many times larger than the initial displacement, which is exciting the system. So now if we increase the frequency even more, I'll skip a little bit ahead. You can see that the different natural frequencies being excited for different system. And so it continues until even higher frequencies, until the most left system is being excited. So I hope this gives you a sort of a feel for what resonance is and what it can mean. Okay, so what is acoustical resonance in piping system? Previously we saw mechanical resonance in a simple setup system. And again, acoustical resonance in a piping system, again it's the excitation frequency equals the natural frequency. And in our systems, there would be the excitation frequency would be the pump and a dampener. And if that excitation frequency determined by those two aspects equal the natural frequency, resonance can occur. And that means that pressure pulsations can increase significantly when that happens. So back to our roadmap. I'll go through each of these aspects involved in a pulsation and vibration analysis separately to see what kind of impact and what kind of aspects you should be looking at when looking at pulsations and vibrations. So we'll start with our initial acoustic excitation. This basically excites our systems and determines our exciting frequency, which is the pump. So a little bit working principles of a reciprocating pump. I assume most people already know the working principles of a reciprocating pump, so I won't go into that much detail. But on the left you can see the suction phase of a pump, so the piston pulls out of the cylinder head and sucks in water or any other liquid. And on the discharge phase, the valve at the bottom closes, the piston moves back in and pushes all the water out, and the valve at the discharge side opens. And this repeats, and for the suction the outlet valve closes and the inlet valve opens. On the right you can see a flow profile, a simplified flow profile of a reciprocating pump for a single cylinder. So here you can see initially, if we follow the red line for example, initially the piston pulls out and the flow is 0, and then it becomes positive and discharge happens. And when we follow the green line, it's a suction. This is on when the piston moves out, it sucks in water, and then no flow will exit the system through the suction valve after that point. And these sharp peaks are taking into account some kind of left volume inside of the cylinder head, which is causing this delay of valves opening and closing. So what aspects determine the pump flow profile? So we just saw a little bit of a sharp opening or closing characteristic of the valve on the suction and discharge side, which accounted for additional volume in the cylinder head, which is called clearance volume also. But there are other aspects which make up some kind of a flow profile, which is also the conrod length, the crankshaft radius, which cause the flow profile not to look exactly sinusoidal. Also the number of cylinders, of course, clearance volumes I just talked about, and also valve characteristics. These are a lot more detailed problems and not many times they're included in an analysis, and also the fluid properties. So just to give you a couple of examples, I generated these plots using our own software for pulsation analysis, and this is a flow profile of a single pump, simplified. So you can see on the left you see the flow rate, and with every change in flow rate there's a change in pressure, and this is basically what causes those pressure pulsations, because the reciprocating pump has a changing flow profile, which also causes changes in pressure. So if you look at frequency components of such a system, and this is very handy if you're looking at what kind of excitation frequency does such a flow profile really contain. So on the left you see the simple flow profile, and on the right you see all the frequency components of that flow profile. And these frequencies are always an integer times the frequency of your pump times the number of cylinders. There's no chance there will be any intermediate frequencies. So if the frequency of your pump is 5 Hz, your number of cylinder is 3, you always get frequency components at 15 Hz, at 30 Hz, at 45 Hz, and so on. So this pump is a single cylinder and the frequency is 5 Hertz. So you can see the strongest component, so to speak, so the largest flow rate fluctuations contains at the frequency of 5 Hertz. And then you can go to 10 Hertz, there's also quite some components there. Then you go to 15, 20, and at the higher frequencies there are very small amplitudes of those components which are being generated by the pump. And which also makes sense because this flow profile almost looks like a perfect sinusoidal, so you would assume that the 5 Hertz, which is a perfect sine of 5 Hertz, is also the one with the largest amplitude. So now if you look at what kind of effect has the conrod, I just talked about a little bit, it causes the flow rate profile not to look exactly like a sine wave. Because even though your crank rotates like a perfect sine, the conrod length limits that flow profile, and it causes it a little bit to become skewed. So if you look at the right, you can see that the red one is the curve of with a limited conrod length, and then the black one is a perfect sine wave. So you can clearly see a difference in that. So now another example of the number of cylinders. So if you have a triplex, so 3-cylinder pump, you can sort of superimpose those flow profiles I showed previously on top of each other, and you get something like this. So these are this is the flow profile of 3 cylinders firing after each other, and the sum of all those flow profiles causes this final flow profile. And now if you do look at the frequency domain of this pump, you can see that it's no longer at 5 Hertz, but it's at 15 Hertz. And that makes sense because we now have 3 single cylinder pumps, and the rule was you take an integer times the frequency of your pump times the number of cylinders. So now we do, if this pump runs at 5 Hertz, we do 5 times 3, the first harmonic is at 15 Hertz. And other components involve only multiples of this 15 Hertz, integer multiples. So you have 15 Hertz, you have 30 Hertz, you have 45 Hertz, 60 Hertz, and so on. And now you can still see that the component with the largest amplitude is at that first characteristic harmonic, which is 15 Hertz. So another example is the clearance volume. So this is the volume of liquid which is left in the cylinder when the piston is fully extended into the cylinder. And this sort of causes delay effect of opening and closing of the discharge and the suction valves during their cycles. So here you can see this causes a little bit of a jump in your flow profile. So even though the piston already starts to move in again, the valve does not open yet, and only after a slight delay the valve opens and suddenly there's flow going through the discharge valve. And again, this has some effect on your frequency domain analysis. So these peaks all shift a little bit, and most of the time this kind of effect introduces higher frequency components. So here you can see another comparison what clearance volume does with your flow profile. On the left you see no clearance volume taken into account, and you get back a simple, relatively simple flow profile. To the right you see with clearance volume, and here you can see the distinct sharp peaks of the valve delay opening. So now we go back to the roadmap for pulsations. We'll go on to the dampener, and the dampener dampens the initial excitations, and the initial excitation again are the pressure fluctuations corresponding to the changing flow profile of a pump. So several important aspects for a dampener is, for example, the distance between pump and dampener, the volume, which is very well known, the type, so you have different types of dampeners, connection diameter, if it's a side branch dampener, the diameter of the branch is a characteristic of the dampener characteristics, the diameter of the downstream piping. And then you also have other forms of dampening besides a dampener, and that's an orifice plate or something else that causes a significant pressure drop. So on the right you can see just a quick example of how a dampener can reduce pressure fluctuations. So initially we have a pressure fluctuation of almost 5 bar, which is the red peak here at the lowest harmonic. Other pressure pulsations are lower at higher harmonics. And then when we add the dampener, it's almost hard to see, but here in the black you see a circle, and that's around 0.6 bar. So that's with a dampener. So it's definitely a significant change. So here we have an example of what the effect of the dampener volume is. So this is for a specific system. It's not necessarily that this rule applies for all systems, certainly not. Just to give you an idea how your pressure pulsations change with change of volume. So initially you can have a 1 liter volume, you have a 3 bar pressure pulsation, 5 liters 0.8, 10 liters 0.4, and 20 liters 0.2. So it's definitely not a linear relationship. You should definitely take it in consideration, especially if you still have high pressure pulsations in your system and you already have a significant volume dampener. Then you should consider not increasing the volume of the dampener, but instead use other methods of making your dampener perhaps more efficient to lower the pressure pulsation. So it always goes to some power function of the root, and this constant X changes per system. It's definitely not linear. So another example is the distance between a pump and a dampener. So there are also other reasons why the distance should be as small as possible, but one of them is that you have a frequency for natural frequency between the pump and a dampener. And this frequency, I'll go more into detail later on about what the natural frequency is and how you calculate those. But if you place the dampener 1 meter away, you have a natural frequency of 350 Hz, for example, for this system. And that's very high. You can imagine most pumps 5 Hz. If you have a triplex pump, that's 15 Hz. And then you go all your fundamental harmonics is times 1, times 2, times 3. So it takes a while before you get to this very high frequency range. If you place it farther away, like 2 meters, for example, you already go to the 175 Hz. And if you go even lower, you come into the range where your natural frequency actually corresponds to some kind of frequency where your pump still has significant pressure pulsations. And if that's the case, then you can actually have resonance between your pump and your dampener. And this can cause, again, shaking forces, and definitely can significantly reduce your valve lifetime. So it's also always a rule to place the dampener as close as possible to the pump. And then you can go on and look at the pulsation profile at different frequencies. So you can see the red one is 1 meters away, that's far away, or close by. The red one is 2 meters away, that's farther away. And you can definitely see that the pressure pulsation is upstream of the dampener. You can see a significant shift towards the lower frequencies. The same for the pressure pulsations downstream of the dampener. And you can sort of ignore the amplitude of these pulsations, because it depends on what kind of model you use for your initial frequency excitation. We can definitely see a shift of major amplifications at a different frequency. So now that we've looked at the pump and the dampener, we can look at the piping geometry. And the piping geometry actually determines the natural frequency, and specifically the acoustical natural frequencies. So first let's go to the right. We'll discuss a little bit about the typical natural frequencies in a system. So for very simple systems, you can actually identify them yourself. So you have two different fundamental. It's a closed open and an open open. And what this means is closed open is, for example, a boundary condition or the end of a system where the flow is specified. So this could be a dead end branch or something like that. So there's no flow going to that end of the system. And an open condition is then where the flow is not specified. So this is a pressure condition. And then on the right you have your open condition, which is just means you have the similar conditions. So you either have a fixed pressure at one side of your system and a fixed pressure on the other side, or a fixed flow and a fixed flow. And what this means, you can see that how the wave travels through the system and can create a natural frequency. So for the closed open, the pressure will be high and low at one side, and it will be constant at the other side. And for an open, the pressure will be constant on one side and constant on the other side. And these each correspond to a different wavelength. And then you can also go to higher modes, which is just a multiple of the same wave multiplied. So the most important thing is these are the rules of what frequency corresponds to what length. So you can see it depends on factor K, which is basically the fundamental or the second mode. So K is 1 is a fundamental, K is 2 is a second mode, etc. And then you also go the speed of sound, which is important parameters, and then the length of your system from the one boundary condition to the other boundary condition. We can use these rules about frequency and length to sort of see what kind of frequencies can emerge in your system. So most systems are complex, so you cannot directly see just from looking at the system what kind of natural frequencies there are, but you can sort of estimate, definitely estimate what kind of natural frequencies there will be in your system, especially if it's a very simple system, so not that many branches, not that many Ts. So examples for between two similar boundary conditions, which is an open. Here's the formula again for what kind of frequency corresponds to that. Between two vessels, which are both constant pressure, between the vessel and the dampener, which can also be considered as between two fixed pressure conditions. Excuse me. And then you also have between a header box pump and a dead end branch. And these are both fixed flows of 0. Okay, then you have natural frequencies between two dissimilar boundary conditions. This is between a header box and a dampener, so between a fixed flow and a fixed pressure, and also between a dead end branch and a large diameter header. So the large diameter header, most of the time you can see that as almost as a constant pressure, because the change in diameter is so large, effectively the branch sees almost a constant pressure. And again, many more complex modes can exist, and definitely for more complex systems you cannot just estimate the natural frequencies in a system just by looking at it. But it's always a good rule to when you initially design a system, to prevent any of these typical natural frequencies to be in your system initially. So you always want to prevent, again I wrote it down here, you always want to prevent prevent a system where the natural frequency is equal to the number of cylinders times the frequency of the pump divided by an integer. So now that we've looked at the pump, the dampener and the piping geometry, how do you put all of these three aspects together to come up with a final pulsation level in our systems? We'll look at that now. So for simple systems, we can use the equations on the right for closed open and an open system and come up with some estimation of whether acoustical resonance can occur in your system. So this again is only for simple systems. So for example, we have a 3-plex pump, so 3 cylinders. This pump runs at an RPM of 300 and the speed of sound in our system is approximately 1400 meters per second. So first we need to determine the first harmonic. And this is because at the first harmonic you saw the most of the energy is contained. At this frequency the largest peak-to-peak pressure fluctuations are contained in our system generated by a pump. So we want to prevent our natural frequency in our system to match the first harmonic of our pump. So what's the first harmonic of our pump? It's the 3 number of cylinders, 3 times your frequency, which is for an RPM of 300, 5 Hz, so 3 times 5 is 15 Hz. So we want to prevent any natural frequencies at 15 Hz in our system. So for example, in my system I have the distance between the vessel and the dampener of 47 meters. And a vessel and a dampener act like an open system, because they both sort of have a set pressure. So if you go to the right, you go to an open system. The length of such a system is half lambda, And we can use this equation at the bottom to calculate our natural frequencies for such a system. So if we do that, fill out those numbers, we'll get natural frequencies of 14.9, 28.8, and so on. So immediately you can see that the 14.9 Hz is equal to the 15 Hz, almost equal, and you have a high likelihood of resonance to occur in your system. So what if we double the distance between the vessel and the dampener? Again, it still acts like an open system, but now of 94 meters. If we calculate all our natural frequencies for the system, we get the lowest, the fundamental, we get at 7.45 Hz. Then we get our second mode at 14.9 Hz, and so on. And again, 14.9 Hz is very close to the 15 Hz. So again, you have a high likelihood of resonance to occur in your system. The final example, the distance between the vessel and the dampener is 40 meters, and if you fill out the numbers again, you get a natural frequency of 20 Hz, 40 Hz, and so on. And this is a better initial design, because the natural frequencies in your systems are removed far away from the first harmonic of your pump. So again, it's only for simple systems. If you don't have that many branches or T connections, you only have one boundary conditions, one injection point or something like that, one vessel in your system, then you can use this to approximate whether acoustical resonance will occur in your system. If you have more complex systems, you want to use a computer-aided analysis method to capture all these effects. And then also you want to use computer-aided analysis to include uncertainties in your dimensions, fluid properties, and pump RPM. And this is to allow for a robust design. Because you can imagine if your dimensions are a little bit off, your natural frequencies change. If your fluid properties change a little bit during operation, so the temperature of your fluid changes, then the density changes, and then also the speed of sound changes. And this also changes the natural frequencies. And then finally, the pump RPM, you don't just want to have a robust system at 300 RPM and then suddenly have excessive pulsations when you run your pump at 302 RPM. So you should take into account all these small uncertainties in your study. So what kind of type of computer software is out there? On the left you have the frequency domain solvers. These are solvers based on linearized flow equations, and they're relatively fast, but they also have a limited validity, especially when pressure drops are large. So if you have an orifice plate in your system, or you have a partially closed valve, or you have high velocity flow, those all cause large pressure drops in your systems, and you can expect that the frequency domain solvers introduce a lot of inaccuracy in your pulsation analysis. So on the right you have your time domain solvers, and this is actually the type of solver that's implemented in PulsePulse currently. PulsePulse is the pulsation program we developed at DRG. It's computationally more expensive to do simulations with this type of solver, but it also has a larger range of validity. So you don't have the downside of the inaccuracies of the frequency domain solvers. So then, now that we know how to do pulsation analysis, why go further? So if we look back at the main problems due to excessive pulsations, we have the noise and we have the reduced surface life of pump valves. We can sort of cover those by just setting a limit on the maximum pulsations in our systems. But the shaking force is causing vibrations and fatigue failure. You should be more careful with that. Because when you go to the bottom of this slide and look at the last lines, you see when using standard or guideline on pulsation limits, if pulsation limits are met, so if a standard you meet pulsation limits of a certain standard, it does not guarantee that there will be no excessive vibrations or fatigue failure. So if you have a very poorly designed mechanical system, you can still have excessive vibrations even though your pulsation limits are met. But also the other way around, if your pulsation limits are exceeded, so that you exceed the pulsation limits set by a certain guideline or standard, excessive vibrations and fatigue failure are not guaranteed to occur. So you still might have safe operations. And you can imagine if you have a very, very strong mechanical system, you can actually absorb all those pulsations without any vibrations. So therefore we'll look at the vibrations now. And the main thing is that they cause shaking forces. And this is basically a whole new system where resonance can occur, and this is mechanical resonance instead of acoustical resonance. So we start off by looking at the shaking forces caused by the pulsations, and this is basically the initial excitation for the mechanical system, where the pump was the initial excitation for the acoustical system. So what are shaking forces exactly? Shaking forces are caused by temporal pressure differences between elbows. So if you look at the figure to the right, you see two elbows, and at one elbow you have P1, at the other elbow you have P2, and if the pressure at P2, for example, is much larger, which can happen when you have pulsations traveling through your system, there's actually an effective unbalanced force or shaking force trying to move the whole pipe towards the right. And because it's the pulsations fluctuate from positive to negative, we call it shaking forces because it attempts to try to move the pipe to the right and to the left and back and forth. Okay, and these forces always act in the actual direction of your pipe. So those were shaking forces, and now we look at the mechanical natural frequencies of the system, and these are determined by the piping and supporting of such a system. So just some typical mechanical natural frequencies. You have an expansion loop on the left, and it's poorly supported. Then there's most likely some kind of mode which tries to move the whole header section of the top horizontal section towards the left and the right. That's typically a natural frequency then. In that case, you should place an actual stop or something inside this expansion loop to prevent that natural frequency from occurring. Another typical natural frequency from a mechanical point of view is the vibration of unsupported branches. So in the picture you see some kind of branched valve. On the left it's unsupported, so that will definitely start to vibrate, or very likely to vibrate. And on the right you properly support that on your piping itself, and this will definitely reduce eliminate the natural mode. And a little note on the below, you should always be careful using relative flexible supporting structure. For example, if you have an actual stop at a 4-meter T-post, you cannot consider that stiff, and it might work for a static condition, but it's definitely not sufficient to retain a pipe if there's shaking force applied, because the whole T-post will just move along with the piping. So now we've discussed the shaking forces and the piping and supporting, so now let's look at the actual vibrations. So again, in a mechanical sense, a mechanical resonance can occur. So I try to illustrate this sort of with the picture on the left. So on the top you have the pulsations. You have the amplitude of the pulsations, and then on the horizontal axis is the frequency. So for example, the most left is the 15 Hz of our system, and the second peak is the 30 Hz, which is the characteristics of our system, and then you have 45 Hz. This is for a pump at a 5 Hz frequency with 3 cylinders. 3 times 5 is 15 Hz. Okay, then you have below that you have a graph of your mechanical resonance modes. So these are basically only signify the locations where at which frequency a natural frequency can occur. And then below you have the amplitude of the mechanical vibration towards the frequency. So you can see that our initial peak, there's no overlap in our mechanical resonance modes. So we call this a forced response. So there's still some vibrations, but they're not that significant. And especially if you look at our second mode, which for example was at 30 Hz, you see it overlaps with the mechanical resonance mode, and then actually resonance will occur. And this causes the mechanical vibrations to be amplified largely. So this is resonance, and you can see this peak is many times larger than the force response, even though the initial shaking forces were almost equal. And the last one is a force response again, because it doesn't really overlap with any mechanical resonance mode. And you should definitely take into account that if you would apply the shaking force as a static force, you would get a much lower vibration, and so the mechanical resonance can actually amplify that static force effectively and cause many times larger vibrations. Okay, so this is basically covers all of the aspects in the pulsation and vibration analysis. I've covered the pump, which causes the initial acoustic excitation, a dampener, which we try to dampen the initial excitation in the piping geometry, which determines our acoustical natural frequencies. Okay, and those combined determine the final level of pulsations. If acoustical resonance occurs, you can expect large pulsations. Then we go one step further. Pulsations, they can cause noise and reduced valve life, but they can also introduce shaking forces. And shaking forces are basically our mechanical excitation. And we compare that to the natural frequencies of our piping and supporting, and those combined will determine the final level of vibration. And these vibrations can cause fatigue. So I just want to end up with a little bit of design improvements for pulsations and vibrations. So first of all, pulsations improve the efficiency of your dampener. Okay, you can increase your dampener volume, but as I showed before, sometimes this is not an effective option anymore. So you should try to improve your efficiency of your dampener in other ways, such as reduce the distance between the dampener and the pump. And another one that also works is increasing the connecting diameter to the dampener relative to the downstream piping. So if you have a branched dampener, you want to try to increase the neck of that branch compared to the downstream piping. And another one is to eliminate or dampen acoustical resonance modes. So you want to avoid system lengths at the lowest harmonics. Most of the time you can only do this during design stages. And you can also place an orifice, and this sort of breaks a natural frequency of your system by introducing a large pressure drop. Design improvements to reduce vibrations. First of all, reduce the pulsations. This is probably the easiest way. But if that's not possible because you're already fixed on your design of your acoustical system, then you can also try to eliminate or dampen mechanical resonance modes. Okay, and this mostly is done by adding or changing supporting. So you always want to restrain your piping as much as possible so it cannot vibrate. Another is to stiffen your support structure. In the example, if you use a very long T-post, that's not a really good support. So you definitely want to stiffen the supports as much as possible. And one of the rules is in these type of systems you always want to use as much as on-ground supports as possible, because that's then you can really realize a very stiff support, and you know that if you put it in an axial stop, it will actually prevent your whole piping system from moving axially, even at different frequencies and different shaking forces. And at last resort, you can use a special supporting. So this is special dynamic supporting, and I won't go into too much detail, but it acts differently under static loading than it does under dynamic loading. And this is most of the time possible. Now you can really sort of restrain your piping dynamically and not statically. So this is better for when you have large temperature differences. So this will conclude the webinar. I hope you enjoyed it, and I hope you learned a lot from it. We also, I just want to remind you, we also offer training courses. We also have a program Pulse for pulsation analysis, and then we also conduct our own pulsation studies. So here are just the links if you're more interested in our services. And also, if you like the webinar, please follow us at LinkedIn. So thank you for your time.